This is the third lecture from Chapter 13, and this lecture is over integrated rate law. The differential rate law, which is the one we talked about in the last lecture, and the more common of the two, talks about the rate of a reaction at different concentrations. And the integrated rate law, which is the subject of this lecture, is also going to talk about the rate of reaction, but it's going to be versus time instead of versus the concentration. So one of the things you want to associate is when you see differential rate law, it's, if you remember, called the method of initial rates. Okay, that's when we made a tangent line at the very beginning of a reaction and then do repeated trials to determine the order of the reactions. So, but if you want to predict the rate of a reaction at any time other than time equals 0, the initial rate, the differential rate law won't do that for you. And of course, chemists want information about the rate of reaction at different times, so therefore we have integrated rate law. And so just to kind of give you a glance at the difference, the first one, and I guess since it's the more common one, is just called the rate law, but this is really the differential rate law in this middle column. And then over to the right is the integrated rate law. And integrated rate law is literally, if you've taken calculus, it's literally integrating the differential rate laws, which you are not going to need to do. So as a quick summary, the differential rate law monitors rate as a function of concentration. Integrated rate law monitors concentration, so that's the same, but as a function of the time of reaction. So let's look at the different plots for these. The differential rate law, which is rate versus concentration. We haven't talked much about zero order reactions, but you should know by now that if something is zero order, that means that the rate of the reaction does not depend on concentration at all. There's a set rate and it remains constant. So that's what you would expect. Graphical interpretation is pretty important in this unit, so make sure that you understand how to interpret these graphs. A first order reaction means that the rate of the reaction is directly proportional to the concentration of that reactant. Okay, so you expect to see a line. Okay, that's what directly proportional gives you. Second order, that's when the rate is exponentially dependent on the concentration, and that's where you see an upward curving line. Now the integrated rate law, we're going to use graphs even more than we did in the differential rate law. Notice also what's on the x and y axes of these two graphs, whereas concentration of a substance is on the x-axis for the differential rate law, shows up on the y-axis for the integrated rate law. And so pay attention to what's on the axes. For the integrated rate law, time is along the x-axis. Zero order reactions, those that are not dependent on any concentration, are linear. And first and second order have a curve to them. All right, so I'm going to go into a little bit more detail about zero, first, and second order. Most of the reactions in real life are either first order or second order. There are some that are zero order, though, so I'm going to start with that. Again, make sure you understand what zero order means. It means the rate of a reaction is not dependent at all on the concentration of a reactant. So basically, the rate in this case is equal to the rate constant. So here's the differential rate law. You don't, since anything raised to the 0 power is 1, you don't even have to show that. Okay, I'm just reminding you. So differential rate law for zero order, the rate actually equals the rate constant. The integrated rate law for zero order looks like here. And I want you to notice, because it's important understanding integrated rate laws, that all of the integrated rate laws are shown as the form of a line because they're typically graphed. So if you remember, hopefully from high school geometry, algebra, I don't know where it first shows up, the form for a line, y equals mx plus b, where y of course is what's plotted on the y-axis, and x is what's plotted on the x-axis, m is the slope, and b is the y-intercept. Okay? So that'll kind of help you figure out what you need to know from these integrated rate laws. So again, concentration, this is zero order only. Each of the orders have their own integrated rate law. But for zero order, concentration of a species is on the y-axis. Time is plotted on the x-axis. The slope of is negative k. And then the y-intercept is the initial concentration. This little zero here always means initial. All right, for a first order reaction, of course, here's the differential rate law. Here's the integrated rate law. Let's look at our generic formula for a line. Okay, so in this case, in the y-axis, instead of just concentration, it's natural log of the concentration at a certain time. The slope is the same, though. Slope in zero and first order are minus k, minus the rate constant. And so I guess you need to remember what belongs to what. These are something you have to memorize. I probably will put the various rate laws on your next test, but I won't identify them as zero, first, and second. All right, so again, all of these integrated rate laws are put in the form that allow you to get a straight line from them. And so this is the form of first order that allows you to draw a straight line. All right, so let's look at the graphs. For a first order reaction, if you plot natural log of the concentration on the y-axis and time on the x-axis, you will get a straight line. Your slope will be negative. The slope is equal to negative k. And this is really how you identify from a graph whether it's zero order, first order, or second order. You look which graph gives you a straight line. Now look if you forgot what to plot to get a straight line from a first order reaction. Let's say you just plotted the concentration of a substance instead of natural log of concentration. You wouldn't get a straight line anymore. You get a downward curving line. When can you plot, let's make sure it's sinking into you, when can you plot concentration versus time and get a straight line? When does that happen? That happens with zero order. Okay, so you may want to make some on this. All right, so here's kind of a little concept map summarizing what you should know so far. If you can make a graph of just the plain old concentration versus time and you get a straight line, it's zero order. If you don't get a straight line, it's first or second order, okay? If you take the natural log of the concentration and you get a straight line, it's first order. If neither of these graphs gives you a straight line, then it's most likely second order. Okay, before I go to second order, I'm going to show you a typical type of problem that you would need to work. There are quite a few math type problems you'll have to work with integrated rate laws. So here's a typical reaction. Breaking down sucrose, table sugar, into glucose. This reaction is first order with respect to the sucrose, the rate constant. Notice the units of the rate constant. I'm not sure if you remember, but in the last lecture I told you that units for rate constants are really important. If you're one to memorize rather than derive, you may want to memorize that the rate constant for a first order reaction is always 1 over seconds, which of course is the same thing as seconds to the minus 1. All right, so the question they're asking here is they're giving you the initial concentration, that's at sub-zero, for sucrose is 0.4 molar, and they're saying what is the sucrose concentration after 2 hours. typical integrated rate law, I point out to you right now, if you ever see a problem that asks you about time, it's an integrated rate law you need. Remember, time does not show up in the differential rate laws. So let's look at how we would work that. This is just repeating the problem so you have it in front of you. So they told you it was first order. They ask about time, so hopefully you figure out, okay, I need the first order integrated rate law. So half the problem here is just identifying what formula you need. Once you have that, you plug in the values you have. You're solving for the concentration of sucrose at a certain time. Okay, 2 hours actually. Plug in the information you know. They gave you the rate constant. Make sure, don't forget the minus sign there. Times the time. Now the rate constant has units of seconds, so you've got to convert the 2 hours to seconds. That's where the 7,200 seconds come from. And then the natural log of the initial concentration of sucrose, which they gave you, 0.4 molar. All right, so do all this math here, and you get minus 1.36. Now, in case you don't remember how to get rid of a natural log, what you do is you raise both sides of the equation, use the natural e, so raise both sides of the equation up to e. So it'd be e raised to the natural log of sucrose. E obliterates the natural log, so now you just have concentration of sucrose on the left side. And then e raised to the minus 1.36. Be really careful with these signs. If you plug this into your calculator, make sure you find your e, and you can do this and you know how to do it before you get on the quiz or test. E raised to the minus 1.36 is 0.26 molar. That is the answer. All right, why don't you try this on your own? So I would suggest pausing the lecture, and then on the next page I'll have it worked out. So if you need the information from it, what do we say? We said that the original concentration of sucrose at time 0 was 0.40 molar, and that the rate constant is 6.2 times 10 to the minus 5, 1 over seconds. And I'll just go ahead and write out the first order integrated rate law for you too. So it's natural log, the concentration of sucrose at time t, that's what you're solving for, equals minus k times the time you're talking about, plus the natural log concentration of sucrose initial concentration at time 0. Okay, go ahead and plug in, see if you get it right, and then check your answer. All right, so I went ahead and plugged in all the appropriate values. In this case, they gave you the concentration of sucrose at time t. And of course, you know the initial concentration of sucrose, 0.4. And here's the K value. That doesn't change. It's a constant unless you change temperature. And we're solving for T this time. So how do we arrange this to solve for T? The first thing you want to do is add 0.916 to both sides. Okay, and get rid of that. So I'm going to go ahead and do that. Oops. I am working it out as I lecture. So now we have minus 0.284 on the left side of the equation. Okay, and I'm going to divide both sides now by minus 6.2 times 10 to the minus 5. Get rid of that. I need to write smaller. Okay, and so then that gives us on the left side of the equation 4,580. What are the units for time in here? I kind of left them out of here just for simplicity, but they were seconds. And so let's say that I was asking you for hours. So of course you would just convert that to hours. If you're converting it to minutes, you divide by 60. And if you are converting to hours, you would have to divide by 60 again. And so the final answer is 1.27 hours. Okay, hopefully you got that right. Here we go. All right, now I'm going to talk about second order rate law, second order reactions. The differential rate law for that looks something like this, or if you had two different reactants that were each first order, it might look something like this. So both of these reactions would be second order overall. The integrated rate law for second order it's actually a pain to work with, but here it is. So how would you get a straight line? What would you have to graph to get a straight line for a second order reaction? This, of course, being in the form of y equals mx plus b. You know what? I think it might be easier for you to visualize if I have the kt first plus 1 over concentration of A naught there. But I'm going to move down here. This tells you that if you plot 1 over the concentration of the substance on the y-axis, and time, if you haven't noticed, time is always on the x-axis for integrated rate laws, that you will get a straight line, this time with a positive slope. This is positive kt instead of negative. And the slope is equal to the rate constant. That's a second order. Much nicer graph than I made. All right, so let's compare them all. I love this table. It has all the information. You may even want to print this out. Here are the differential rate laws for 0, first, and second. Here are the units for the rate constant for 0, first, and second. And integrated rate laws, here is the graph you would make from the integrated rate law to get a straight line. And we haven't talked a lot about half-life expressions, but that's actually important also. One of the things I want to point out here is that half-life for a first-order reaction is independent, doesn't have the concentration of the substance in it. So what does that mean? That means half-life for a first-order reaction only is constant. Half-life does not change. Remember the definition of a half-life. It's the amount of time it takes something to decompose halfway, for half of it to decompose. But look at the half-life for a 0 order and a second order reaction. Both of them have a concentration factor in them. Okay? What that means is the half-life for 0 order and second order are not constant. The half-life changes with time. Okay? So that's just important to know. And radioactive reactions, nuclear decay, are first order. Okay? Okay, so we're going to talk about the graphs a little bit more for integrated rate law. They are especially important. It's real common for me to show you a number of graphs with different types of lines on them and ask you to identify the order of each of them by the way the graph looks and by what's plotted on the y-axis. But the bottom line, very simply, is if the concentration of a substance versus time is linear, it's a 0 order with respect to that substance. If a plot of the natural log versus time is linear, it is a first order with respect to that substance. And if plotting the inverse, or 1 over the concentration versus time, gives you a straight line, it is second order. death here. All right, let's talk a bit more about half-life. Again, half-life is the amount of time it takes for a substance to decay by 50%. So let's say that we have, we'll just say for argument, we have 1 gram of something. And when half of that decays, we'll have 0.5 grams. So half-life is the amount of time it takes for half of that to decay. Okay, so it is a time factor. Half-life has units of seconds, minutes, hours, days, some unit of time. It's important to do a number of half-life problems because sometimes they're in percentages. When you've decayed by half, you decay by 50%. And so get familiar with these fractions equating to percentages. When you have 2 half-lives, you've decayed by 1/2 times 1/2, or 1/4. Okay, you only have 0.25 left, or 25% left. When you have 3 half-lives have passed, that's 1/2 times 1/2 times 1/2. 1/8 is left, or 12.5%, and on and on. I recommend memorizing these half-life equations. You can derive them. So, for example, if you have a first-order reaction, if you have the integrated rate law, you can easily derive the half-life expression for first order. If you realize the whole key to being able to derive this quickly, which you do not need to be able to do, you can memorize these half-life, whoopsie daisy, these half-life expressions if you want to. But the derivation, if your memory stinks like mine does, depends on realizing mathematically what half-life is. And so what it is, okay, so the concentration at when the half-life has been reached is simply 1/2 times the original concentration. So if you realize this relationship, and so you plug in wherever you see A sub t, you plug in for half-life, you plug in this value, you can easily get the half-life expression. So you would just come over, for example, to this first order expression. And again, wherever you see concentration of A sub t, you plug in this half-life. So it'd be natural log of 1/2 concentration of A naught equals minus kT plus natural log of A naught. And then simplify this, you would end up with your half-life for a first order reaction. We're going to take a little diversion in the next lecture off to radioactive decay. If you notice on our syllabus day by day, we are supposed to venture off into, can't remember what chapter it is, might be a little bit of 19, but it's radioactive decay. I guess it fits kind of nicely because radioactive decay decays our first order. And why is radioactive decay first order? Well, because if you imagine an unstable nucleus, unstable atom, which we really have shown right here, it doesn't depend how much of that unstable atom you have. The fact that it's going to decay only dependent on the rate constant itself. No collisions need to happen for it to decay. It just sits there and falls apart. So that's a classic first order. It means it doesn't depend on anybody else. It depends on its own self. So this slide goes over in a bit more detail how you could derive the half-life expression for a first order reaction. And as I said in the last slide, the key is to realize what half-life is. Okay? Half-life means that the concentration of some substance A is 1/2 its initial concentration. So as long as you realize that relationship and then substitute that into the integrated rate law expression, you can always get the half-life expression yourself. So here's the first order integrated rate law. Here is substituting in that relationship. Then this is just rearranging. And then finally, natural log of 1/2 equals 0.693. So that's where it comes from. Here's a typical half-life problem. They give you the rate constant. They tell you that it's first order. So you can I will not give you half-life equations on your tests and quiz. So you either need to memorize them or learn to derive them. But if you do remember the expression for half-life for the first order, really simple. Remember, there's no concentration expression in it at all. All you need to know really is the rate constant, because half-life and rate constant for first order are inversely proportional. So if you remember the expression for the half-life, you can work that out in about 30 seconds. If you don't remember the expression for half-life, you can still work it out by using the full integrated rate law. I told you it's first order, as long as you remember to use the right first order. And what you would have to do is, let's see, call the original concentration of the material, just call it 1. Okay. And then you would call the concentration, since you're talking about half-life, half of whatever the original amount was. So this would be 0.5. Plug in the rest of the values and you could still get the right answer. Just take you a little bit longer. Okay, so a couple more slides on our diversion about radioactive decay, which is first order. A common application of that is, you've probably heard of it, radiocarbon dating. And so anything that was living at one time, scientists can do radiocarbon dating on to determine when it died or how long it's been dead. And that uses carbon-14. It's a heavy isotope of carbon. And carbon-14 is produced in the upper atmosphere, and it just kind of gets integrated. Anything that lives and goes through the respiration cycle gets a certain amount of carbon-14 incorporated in their body, along with the carbon-12, the more common. But then as soon as somebody dies and they stop respirating, they don't take in any additional carbon-14, and the carbon-14 that was in their body starts to decay with first-order kinetics. And so depending on how much is left, scientists can determine when they died. The half-life for carbon-14 is 5,730 years, and that's why sometimes they'll get like fossils from thousands and thousands, tens of thousands of years old, and they can date it using carbon-14. And what that means is that if you start with, let's say, 1 gram of carbon-14, in 5,730 years, you'll have 0.5 grams. So here's an example, carbon-14. And so make a note to yourself, anytime a question mentions radioactive decay, make a note that it's always first-order kinetics, so that you use the first-order integrated rate law. And so this is saying 58% of the carbon-14 that's normally in a living thing is left. So how old is the sample of that wood? The way I like to work these problems is to give them actual numbers. And since the natural log of concentration at some time compared to the natural log of the original concentration is always a set ratio, you can make up imaginary numbers and you'll still get the right answer. So if we assume the original amount of carbon-14 was 1 gram, so that would be A sub naught, and then the amount of carbon-14 at time t would be 58% of 1 gram, or that'd be 0.58 grams. So if you just plug those values into the first order rate law and solve it, you get that the time is 0.54 over k, and so we need the rate constant to complete this problem. So here's the expression for half-life for first order reaction, and from this we can rearrange and solve for the rate constant k. The problem gave us it should have given you the half-life for carbon-14. I may have left it out, but we know what it is, 5,730 years, and that tells us that the rate constant for carbon-14 radioactive decay is 1.21 times 10 to the minus 4. Remember that the units for first order rate constant are always 1 over time, so in this case it's 1 over years. Now that we know what k is, we can go back into and solve for the time it takes for 58 to reach 58% of the original carbon-14, and that tells us that 4,500 years. All right, I'm going to give you a couple more examples of problems. Here's a typical one for a second order rate law. And again, the whole key, when any problem asks you about time, they're talking about integrated rate laws. And so the whole key is knowing which of the integrated rate laws to use. This one tells you that it's second order. And so it asks you to calculate the concentration of NaCl after 30 minutes. So really you just need to write down the second order rate law and plug and chug. So the second order rate law. All right, so the second order rate law, I've written it down here at the bottom. And just plug in the values. They gave you all the values you need. And just be a little careful of the math if you're doing a second order because it's 1 over. It's just more places to make silly errors. But plugging in the information that the problem gave you. And again, units. The rate constant for a second order reaction, the units are always 1 over molarity times time, in this case seconds. Pay attention to the time units, make sure these match so they cancel. Anyway, the final answer is concentration of A is 0.018 molar. Here's another very common type of problem for integrated rate laws and their graphical interpretations. Remember what you plot on the y-axis for an integrated rate law in order to get a straight line. So if it's zero order, you simply plot the concentration of a substance. If it's first order, you plot natural log of the concentration. And if it's second order, you plot 1 over the concentration. And so you might be given a bunch of data of time versus concentration and asked to determine what the order is. What you would have to do then is you would literally have to plot this data, time versus concentration. If it did give you a straight line, it would be zero order. In this case, obviously, it doesn't give you a straight line. So then what you would have to do is take the natural log of the concentrations, calculate those, and plot natural log versus time. If that gave you a straight line, it would be first order. If it didn't, you would have to do another set of calculations of 1 over the concentration and check to see if it's second order. In this case, as you can see, if we plot the natural log of the concentration over time, it's also not linear. But if we plot 1 over the concentration versus time, it's linear. And so this, in fact, is a second order reaction. So you need to be able to answer that type of question also. Last slide. Here's the whole concept map. I kind of like this. The first time I showed this to you, I showed you a piece of it up to here. And now we've talked about second order, which just says if you graph 1 over the concentration and it's a straight line, it's second order. And if it's not a straight line, it's too funky for us, so you can ignore it. That's it for this integrated rate law. Make sure you take the quiz in learning catalytics.